Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to lecture 19, Organic Chemistry 3. This is an English version. In this lecture, we continue on terpenes and terpenoids, general methods for the determination of structures of terpenoids. First method, analytical method using spectroscopy. So, mass spectrometry, MS, fast atom bombardment spectrometry, affords the exact molecular ion peaks along with diagnostic fragmentation pattern of the terpenoid molecule. It is an important tool for the structure determination. FAB MS in both positive and negative modes, combination of GC-MS or HPLC-MS spectrometry coupled with computerized analysis and tandem mass spectral analysis have been employed in recent years for the structure determination of various terpenoids. You can have a look at extraction and mass spectrometric characterization of terpenes recovered from olive oils using a new adsorbent assistant supercritical carbon dioxide process published in Foods, year 2021, volume 10, page 1301. Also, you can look at the search structure of the terpenine 4-ol using its fragmentation energy profile case study for GC-MS analysis of the lavender oil, published in Scientific and Technical Bulletin series, Chemistry, Food Science and Engineering, year 2018, volume 4 to 7, page 4 to 7. Let us look to the mass spec electron impact of 4-terpenine 4-ol. The molecular ion cation radical appears at 154 for the molecular ion. We have peak at 139 and peak at 137. We can explain the 147 due to the loss of hydroxyl radical, 139 for the loss of CH3 radical, 121 for the loss of water from the 139. Well, for the loss of the isopropyl or propyl radical, here we have peak at 111, very intense. Okay, so if we get the cation radical on the oxygen, then loss of ejection of isopropyl, we get 111. A resonance with this form, then loss of water will give peak at 93. Again, very intense. If we get the molecular ion in the open form, then proton transfer, then cleavage in this carbon-carbon bond to form a cesium ion, highly stable ion, as we have learned before. Go and listen to the playlist of mass spec from A to Z. We get the cesium ion at 71, and that's the base peak. Since in the structure contains cyclohexene, so we expect retro Diels-Alder to occur, and then we have possibility of the formation of 86, here it is, or the peak at 68, and we have again intense peak. So the structure, the fragmentation of the structure terpenine for all, as it has been proposed and confirmed, of course, agrees with the structure. The fragmentation agrees with the structure based on the basis we have learned from mass spec fragmentation. The second method, ultraviolet spectrophotometry, UV. In terpenes containing conjugate dienes or alpha-beta unsaturated ketones, UV spectroscopy is very useful tool. The values of lambda max for various types of terpenoids have been calculated by applying Woodward's empirical rules. There is generally good agreement between the calculation and observed values. For example, we have here isomeric structure of C10H16 terpenoid, myrcene acyclic terpene, and beta philandrine monocyclic monoterpenes. Well, if we go to calculate the lambda max, since we have diene, so the base value is 214. On the conjugated diene system, we have only one alkyl substituent, so we add 5 for that, so the total will be 219. And the observed value for lambda max for this compound is 224 nanometer. Well, for the monocyclic analog, here we have a conjugated diene system, and it is heteroannual, means the diene double bond is not on the same ring. So again, we calculate the base value of 214. We have here on the diene system, we have here substituent, we have here another substituent, so we have 5 times 2 for the 2 alkyl substituent. We have here double bond going to the ring, into the ring, so it is exocyclic double bond, so we add 5, and the calculated value here is 229, and the observed value is 232 nanometer. As we can see clearly, this value is not at this one, and this is close to that, and this is close to that. You can go and read more and listen more lectures on the UV. Here is a playlist. For the levobimeric acid, we have here again diene, but double bond is homoannular in the same ring, so we start with base value 253. On the double bond, we have here 1, 2, 3, 4 alkyl substituent, so we have 5 times 4, 4 alkyl substituent. We have here this double bond, again is exocyclic double bond, so we add 5. The value is 278, and the observed value is 272. The other isomeric structure here, we have the double bond. The double bond is heteroannular, so we start again with 214. We have here 1, 2, 3, 4 alkyl substituent, 5 times 4. We have this double bond, exocyclic to this ring. So we add 5. So the total is 239, and observed is 237. Well, they are matching well, and here they are matching well, and there is a difference, clear difference in the lambda max value. The third tool is IR spectroscopy, which is useful in detecting groups such as hydroxyl group, which shows up at 3400 cm-1, or an oxo group at 1750 to 1700 cm-1. Just an example, here is menthol, which has an OH. In infrared, you can see clearly a peak at 3362 for OH stretching. It's broad and strong. Also, because you have here all this carbon hydrogen, carbon sp3 hydrogen, it will show up below 3000 cm-1. Okay, for more you can listen to the playlist here for the infrared lectures. Here is benzoin, which has C double bond O. The infrared shows clearly peak, very sharp and strong at 1711. Again, you can see here also the CH stretch carbon sp3 hybridized. Below are 4 spectra that correspond to these terpenes from 1 to 4. Match them up briefly, annotate the spectra, and explain your reasoning. Here we have aromatic, and alkyl group. Here we have OH, alkene, CH. Here we have alkene, aromatics, and OH. Here we have alkene and sp3 carbon H bond. The first spectrum shows peak above 3000 cm-1 for carbon sp2 hydrogen stretch, below 3000 for carbon sp3 H stretch, and around 1640 cm-1 for carbon double bond carbon stretch. Among these 4 structures, this one matches 1. This spectrum shows peak above 3000 for carbon sp2 H stretch, below 3000 for carbon sp3 H stretch. We have here sharp peak for free OH stretch, and another one for the hydrogen bonded one. Well, if we have OH, then we are expecting structure 2 or structure 3. So we have to examine the area of 1600, 1400 for carbon double bond carbon, and the area of the carbon double bond carbon of aromatic. Well, still here we have something in here, but here we have only sharp around 1490 or 80 cm-1. It's not multiple peaks, but just only sharp peak, which means that the most likely the structure will be this one. Well, keep in mind that we have to watch for the other one and compare later on. Here again, we have here an OH stretch. We have the carbon sp2 H stretch, carbon sp3 H stretch, and if we look for the aromatic area, yes, we have here the overtone peak for the carbon-carbon aromatic from 2100 to 1660, and we have, when we look for the area of 1600, 1400, we have, as we can see here, multiple peaks, which mean that it's supporting the structure 3. So you were right to assign structure 2 for the previous spectrum. For the last one, here we have carbon hydrogen stretches. We have overtone for aromatic. We have here aromatic carbon, double bond carbon, multiple peaks. Well, that's number 1. Yes. So we have assigned all the spectrum. Okay, and we can use the infrared to differentiate between these structures. NMR spectroscopy, nuclear magnetic resonance spectroscopy, is one of the most important tools for determining the structure of organic molecules using 1 dimension and 2 dimension, 3 dimension NMR. Here is a YouTube playlist for NMR you can watch. In the previous NMR lectures, we used to provide you with the spectra and ask you to predict the chemical structures. Well, this time I will provide you with the spectra and structure and ask you to assign the signals. Well, given the structure and NMR spectra, assign proton, carbon 13 chemical shifts for camphor. This was published in Chemica Nova 2007, volume 30, page 2053. Camphor, a good model for illustrating NMR techniques. Well, we need to assign the signals. Before we start, I would like to recall that in NMR we have 2 keys to solve the problems: chemical shift and coupling constant. The difference between chemical shift and coupling constant is that chemical shift refers to the shift of the position of NMR absorption that arises due shielding or de-shielding of protons by the electrons of the compound, whereas coupling constant refers to the interaction between a pair of protons. Well, so if we have 2 distereotopic hydrogens on the same carbon, so they have 2 bonds in between, we call it coupling constant J2. Geminal proton-proton coupling, the value is around 20 to 40 Hertz. Carbles found that the relation between 2 distereotopic protons, between them 3 hydrogens, depends on the angle, dihedral angles between these protons. So if we have here bond 2, 3, if we look at it as like a book, okay? The covers of a book. So if we have the book closed, the angle, dihedral angle between A and B will be 0. If the book is open, then the angle will be 180. He found if it's closed, it's around 10. If it's open, it's around 11 to 12, so it's larger. And if the angle between them is 90, then almost the coupling constant will be 0. Well, if we have two diastereotopic hydrogens between them like W or zigzag line, but fixed stereochemistry, it's not movable, then there will be a J4 long-range coupling, J4, and it's about 0.7 to 7 hertz. That will help us in solving the problem. For the comfort, we have here carbon 1 asymmetric carbon, carbon 4 is asymmetric carbon. So this hydrogen on 3, 2 hydrogens, and on 5, 2 hydrogens, and on 6, 2 hydrogens, they will be diastereotopic. They will couple each other, right? With J2. These hydrogens on carbon 3, the less complicated, because it has only one hydrogen in here adjacent on C4. Okay, before I started, I made a model and looked at these two hydrogens and found out that the angle between this hydrogen and this hydrogen is around 90 degrees. So the only coupling will show for this hydrogen will be the coupling with that proton. So expecting that this hydrogen will show up as a doublet, I looked for the doublet in the spectrum and found out that we have here doublet. The value of this doublet is around 18 hertz, which is very close in the range of the J2 value. Okay, so I use this as the starting point for that. Okay, so building the model, this is C4, this is C3, I rotate to see the angle. Here is the carbon 3, and in the back carbon 4, which carries this hydrogen. The angle between this hydrogen 4 and the hydrogen 3N, it's almost 90, so there is no coupling or very small coupling. So I start from this point, assign the peak at 1.84 doublet, it's 18.3 hertz, well, for H3N. As you can see, I assigned all of the proton NMR, but let's see how I did that. Once I knew about the position of H3N, to assign all proton peaks, I used 1H, 1H COSY. I know about the H3N position for sure. Now, H3N should be coupled from the structure with H3X, yes. So this should be H3X, which appears at doublet of triplets. Well, H3X coupled with H3N J2 coupling doublet. Now it couples to H4 with J value of 4.4, and again coupled to H5X long range coupling. See the W structure fixed. KJ4, it was about 4.4 hertz, so H4 and for HX5 have the same J value. That's why shows up as a triplet, so doublets of triplets here. Okay, H3X should be coupled, as we mentioned, with H4. Yes, so here is H4, this one, and H4 should be coupled to H5X. Yes, H5X should be coupled to H6N and 5N. Yes, okay, and 6N and 5N are coupled. All right, and 5N and 6N coupled. H6N and H6X are coupled. It's very complicated in this area. Okay, and we assign all the proton except the methyl. Here we have to go to another type of spectra. I had to use NOE, nuclear over Hauser effect difference experiment. So I irradiate here, or the chemist irradiated at 2.35 for H3X. H3X here at 2.35. When we irradiate, we enhance H3 at 8 position. This is a nearby. Okay, so I knew that this position is belong to H8. Okay, CH3. Well, then we irradiate at 1.95 for H5X. If we irradiate on that, we enhance H9. Yes, so that's the position of H9. Okay, now if we irradiate at H9, we enhance H6X, right? So we irradiate at this position and we get HX. So that's for sure. Now we know that this is H3 at position 9. The rest will be, or the left will be the methyl at position 10. The assignment of the 3-methyl group was confirmed by 2D NOSI experiment. Well, for CH3 on position 8, this should be correlated to H3X and C4H. Well, that's right. We can see the correlation with H4 and H3X. Well, the CH3 on 10 position correlates to H6X, that's right, and the one on C9 correlates to HX6, H5X, and H4. Is that right? Yes. Here we have H6X, H5X, H4X. That's it. We know the position of proton signals, and we would like to assign the carbon 13. For that, we used 1H carbon 13 HSQ-C experiment, which correlates proton to carbon. So for the CH3 on carbon position, here it correlates to the carbon 8 at 19.3. For the CH3, or we call it H10, correlates to carbon 10 at 8.8. Here is proton 9 correlates with carbon at 18.7. Well, here we have H5N on carbon 5, as well as the proton 5X on the same carbon. Right. So H6N and H6X will show up on 2.95 to 9.5 carbon 6. Here we are. For H3N and H3X, at 42.8, the proton 4 on carbon 4, 42.6. Well, and C7 is quaternary, here at 46.3, C1 quaternary at 57.2, and again the carbonyl carbon as expected at 218.8. Before we leave, we had to check the spectra with depth 135 experiment. We know that in this experiment the carbon on CH3 will be positive, CH2 carbon will be negative, CH carbon will be positive, quaternary will not show up. See here, we have 1 CH3, 2 and 3 CH3s. We have CH2, CH2 and CH2, and here is our C4 with HCH matching well. To read more about this interesting subject, tutorial for the structure, elucidation of small molecule by means of E-logic for structure elucidation, LSD software in magnetic resonance chemistry, 2017, page 1 to 11, using artificial intelligence and software to really predict the structure of organic molecules using NMR spectral data. I hope that you have enjoyed the lecture. See you next lecture.